Okay, if you're here, please do the attendance thing on Top Hat. And I don't think anybody's come in since I said this, but there's a pile up here. Just make sure this gets, if you haven't dropped it on the Dropbox, hand it here before the end of class. So Kappa 2 was due last night. Kappa 3, actually, as of about 20 minutes ago, is up and available for your download and perusal. We will, by the end of class today, hopefully have all you need to do the first 13 or so of the 18 problems on this week's set. So you can certainly get started on that over the weekend. Thank you for filling out the reflective writing question this week. Some very thoughtful and complete and well-worded answers, so I appreciate that. I actually teaching a section of Phys 120, the first year experience class this semester. So I think we're gonna take entire class next time, and I might just print out all of them without anonymized and hand them out. So they were so good. So thank you for that. Normally what I would do for next week's, what I did last year for next week's reflective writing assignment would be find a couple of upper level physics majors and get some advice from them about what they suggest you do for this class, which you can still do, and I encourage you to do. Given COVID, though, it's going to be harder to find upper level physics majors. They're not just hanging out in the PLC all day. Sadly, they'd like to be, but we have kicked them out. So I encourage you to do that. I will come up with a different question for next week that will probably be, I don't know, COVID related and how you're coping and things like that. So I'll look forward to that. Questions or comments about any of that? Bailey. That's true. That's true. Part of the exercise, though, was going and seeking out upper level physics majors on your own, meeting them, finding out where they hide, and not being intimidated to meet them. Not that you're intimidated to meet them, I know, but some in this room, believe it or not, might be intimidated to walk up to a junior, senior level physics major. Don't be, though. They're all, with very few exceptions, they're all very nice. You get a group of big enough of any people, and then there are exceptions, but they're a pretty good group. Is there a comment or question there? Oh yeah, the code is 4614. Great. Here's what I'm gonna do. I want a single one. Thanks. And pin that video. That's better. That's what I like. Okay, so where were we? We had spent Wednesday thinking about electromagnetic waves. In other words, a set of fields or time varying fields that might be able to satisfy all of Maxwell's equations in a vacuum with no charges around whatsoever. And we wrote down a couple of things, and we spent Wednesday trying to prove that it does in fact satisfy, the fields that we wrote down do in fact satisfy Maxwell's law for a couple of different scenarios, 2 different Maxwell's laws. And we found that in doing so, if they do satisfy Maxwell's equations, that we know what the ratio of the E to B fields are at any given time in an electromagnetic wave. And we know that the wave speed must be equal to some combination of those physical constants, epsilon naught and mu naught. Maxwell's equations tell us what the speed of light have to be in terms of those fundamental constants of nature. So that's kind of a cool ancillary of all of these things. So it's interesting. These electric and magnetic fields, this is different than you thought about, isn't it? Different than how you thought about these fields last year. Last year, these fields were always associated with charged particles. Electric fields emanating from charged particles, and magnetic fields being induced by charged particles, or in some bar magnet. Here we have electric and magnetic fields in an entirely empty universe that's void of electric and magnetic charges, right? It is possible for these fields to exist, both of them, in areas where there are no charged particles at all. And in fact, these fields carry energy in some real way. They are real in some sense of what the word real is. They're not just things that we use to calculate forces on charged particles. They exist and are real in some very well-defined and quantitative way, in that they carry energy, and that even devoid of other things around, they have some energy. So you have some real world experience with this. Obviously, if you stand outside all day in the hot sun, your skin will warm up, you might get burned. They carry energy in some real way, these electromagnetic waves. So we need to I will stop this. We need to develop some formalisms around the energy of these waves. So this is one of my favorite vectors of all time. You ready for this one? It is the Poynting vector. Actually named for somebody whose last name was Poynting, right? John Henry Poynting, specifically, who lived from 1852 to 1914. And if your name were Poynting, you'd probably want to come up with something that had to do with a vector also, because why wouldn't you? So here's how we define the Poynting vector. It's a capital S, I don't know why, with a vector sign, and it's defined to be 1 over mu naught times the electric field across the magnetic field. What are the units on this thing? What are the units on the Poynting vector? Well, you might not know E and times B divided by mu naught off the top of your head. That's okay. I'm here to tell you what the units on this thing are. They are joules per second times meter squared. Or if you like, and you prefer watts instead of joules, watts per square meter. This is an energy density propagating in a particular direction. So note that, so some notes. One, E cross B is always in the direction of motion. And also, and since E is all for EM waves, we're talking about EM waves here in particular. And since E is always perpendicular to B in an EM wave, again for EM waves, then it's true that S equals E times B divided by mu naught. At least the magnitude of S is equal to the magnitude of the electric field times the magnitude of the magnetic field divided by mu naught, and it points in the direction of wave propagation. I should say the Poynting vector is more general than just being applied to EM waves, but when you apply it to EM waves, those two things are the case. E cross B is always in the direction of motion, and E and B are always perpendicular, so that the vector formula becomes a little bit simpler. The magnitude is EB over mu naught, and it's always in the direction of propagation. Okay, note. Interesting things here. So that's one note, that's one note. Here's another note. E and B and therefore S is not constant in time. I'll say these are all notes for EM waves as they refer to Poynting vector. S is not constant in time. I'm going to underline not. We know that the strength of the electric field is changing at a given point as it goes along. We know the strength of the magnetic field is changing at a given point as it goes along. We know that at the nodes, for instance, E and B are both 0. And therefore, at the nodes, S is 0. And at max amplitude, we have EM and BM, which means that S is E max times B max divided by C. And we even know how E max and B max are related, so we could write this in terms of entirely E max or B max if we wanted to. All we have to do is put a little speed of light in there. So again, Poynting vector is, again, it's an energy per square meter. It is how much energy is associated with the field that we're talking about here, right? So, question. Oh, you're right. That should be me now. Thank you. Yep, you're right. Right. So imagine you've got some wall or some, it doesn't really matter, some square in space, and an electromagnetic wave is propagating through it, right? The S vector, the S value, the Poynting vector through that, in that space, is constantly changing in time as the amplitude of the wave goes up and down. At some point it's 0, and some point it's high. It's like pulses are passing through that particular region of space in that time, as the energy density gets higher and lower as the wave passes by. Kind of like on the ocean, or ocean waves hitting a shore. That energy is being deposited in waves as it comes through. Okay, you may say, aha, I've heard of an electromagnetic wave that has pulses before. Are you talking about these photon things? No, I'm not. This is, I should take a step back. Everything that we're going to be talking about in this class is pre-1910, our understanding of how the universe works, right? This is a completely classical way of describing electromagnetic waves and light. And so I'm not talking about any discrete packet of energy here. I'm talking about a plane wave of classical light, electromagnetic radiation, passing through space. Even that comes in waves as the amplitude of the electromagnetic field change over time. That is different than a quantized unit of energy, though. That is a energy that's spread out over a plane wave as it propagates through space. Okay? We don't know photon. That is not even a word that's been invented yet. I'm not even gonna know what you're talking about if you ask me about a photon. That's next semester. We'll get to it a little bit at the end, but not much. Okay. Right. So these pulses come fast, though, right? Speed of light is incredibly fast. So usually we're not interested in how the energy that's passing through a given point in space is changing over time. We're more interested in the average of the energy that's in a particular space over time. That's often a much more useful thing to know, because almost always we're integrating over some time interval that's way longer than many, many, many of these pulses coming through. So S is useful, but even more useful, these pulses come fast. We often want to know the average. So we define I to be the value, the RMS value of the Poynting vector. And by RMS is short for root mean squared. We're going to talk a lot about root mean squared later on in the semester. For now, just know that this is the RMS electric field, the root mean square of the electric field, times the root mean square of the magnetic field. You can think of root mean square as an average, but it's not really the average, because what is the average of an electric field over the course of a full wave? It's 0, right? That's not useful to us. So RMS is you square the wave, and you take the average of that, which is not 0, and then you take the square root of that. It's the root of the square of the mean, but the root of the mean of the square. Root of the average of the square. This is RMS. So it takes a function that is integrated to be 0 over time and makes it so that you can kind of estimate the value away from the mean that that function has over a full cycle. It's useful for lots of reasons that we'll come back to later on. Anyway, there's our mu naught still there. We know that at any given time, the electric field and the magnetic field strengths are related by C. So we can write this in terms of entirely electric field or magnetic field if we wanted to. So this is also EM squared over 2C mu naught. So two things I've done here. I've changed the RMS electric field into a mean, to a maximum electric field, and I've divided it by a factor of 2. I don't know if you can see this. You certainly can't on Zoom. Let me just highlight it here. This 2 comes from the fact that I've changed this RMS to a maximum. I should probably write this down. ERMS, this is an aside, ERMS equals Emax divided by the square root of 2. That's the RMS of a sine wave integrated over the entire one full wave. You get a factor of square root of 2, 1 over square root of 2. So that's where that factor of 2 comes from in the bottom. And I've also converted my BRMS to an ERMS by dividing by C. So I get an Emax, that's an Emax squared divided by 2 times C times mu naught. And you can also write this, if you want to, in terms of lots of different ways. If you like epsilon naught instead of mu naught, you can write this as C over 2 times epsilon naught times Emax squared, since C and epsilon naught and mu naught are all related to one another. And you can also write this in terms, if you want to, of Bmax. This is also C over 2 times Bmax squared over mu naught, I think. That looks right. It doesn't look right. I'm not sure about that one. Anyway, you can write this in terms of Bmax. Oh yeah, that's probably right. The only difference between Emax and Bmax is a 1 over C. So yeah, I think that is right. C over 2 Bm squared over mu naught. Anyway, you can look that up. Anyway, the point is you can write this in terms of Bmax or BRMS or Emax and ERMS and move back and forth between them because you know how all these things are related to one another. Great. So light carries energy, and you can calculate how much energy it carries. This I is an average energy of a electromagnetic wave propagating through a region of space per square area as that wave is propagated through. So what is I? I mean, why do we call it I? We should think of this as sort of an intensity or a brightness, right? This is how much light there is. It's how bright it is. It's how intense that energy is as it's coming. Okay. It also carries, interestingly, not only does it carry energy, light can carry momentum, which is weird because you probably, from Analyte 1, thought of momentum entirely as terms of mass times velocity. And this electromagnetic wave is just a propagating field wave. There is no mass associated with it whatsoever. So in most classical senses of momentum, you would say that the momentum of this wave is zero. But this wave can carry momentum because momentum is a little bit more general than just being mass times velocity. So, so light can also carry momentum. Holiday, Resnick, and Walker, your textbook spend an entire page deriving the formula for this. You can look at it if you like. They never mention Maxwell's equations. They do a lot of hand wavy stuff. You can look at it if you want to. I'm not going to bother to go through their argument here. I'm going to write down the equation for the momentum of an electromagnetic wave. So here we are. Delta P equals delta U divided by C. So P is momentum. And U is energy. So the momentum change of an object is related to the total energy absorbed by the object from the wave divided by C. So if you got some incoming wave and you have some object that's absorbing that energy from that wave, it's imparting some momentum to it based on dividing by number by C. Say that again? Yeah. Right. Yeah, I see what you mean. You get E equals MC squared. Certainly the units work out for doing it that way. Yep. I don't know if that's what inspired Einstein or not. It's an interesting point. That's all right. That's all right. Oh, I remember what I was going to say. Just so you're aware, there's going to be a lot of symbol ambiguity in this class. P is by far the worst offender of all of them. So I can think of at least 5 different things that we're going to use P for in this class. I will try to be explicit every time I'm writing down P, and it will probably be pretty obvious from the context most of the time, but not always. So if you ever don't know what something is and I write down a P or any other symbol and you don't know what it is, please stop me and ask, what the heck does that P mean? This one's momentum. Okay, so the wave itself carries momentum. A piece of wave carries a momentum that is proportional to the volume in consideration. So also from HRW, your textbook, you can look this up. The force, so again, this is the force applied to an object as it's being struck by an electromagnetic wave. That force is equal to the intensity times the area divided by C. So here force, F equals force. I is as above, the intensity. We defined it above. And A is the surface area of contact with that electromagnetic wave. And C is the speed of light, of course. So we can write this as F over A equals I over C. Now, this is a point at which every other time I've taught this class, we would have just finished our segment on fluids. And I can see now, this is a point at which It's important to have had fluid to know what an F over A is. Does anybody know, though, before we take fluids, what force divided by an area is? That's a pressure. If you have a force divided by an area, that's a pressure. Even the units on pressure that you may be familiar with, if you're pumping up your bicycle tire, what units do you use for pressure? That is definitely a force, that is definitely a measure of pressure. Not usually the one that's written on your bicycle pump, but sometimes it is. Pounds per square inch is another unit of pressure that's probably more likely what you have on your bicycle pump and is more useful for understanding the definition of pressure as force per unit area. Pounds per square inch. Pound is a force, is a unit of force, not a unit of a mass. It's a unit of force on the scale as you're weighing yourself. Pounds per square inch is force per unit area, and that's what pressure is. It is how much force is being exerted per square inch or square meter or square kilometer or whatever it is of the surface that you're looking at. So F over A is pressure. So we can define something called radiation pressure. There it is. I've already used P. We're only 3 lines down, and I'm already using P for something completely different. I'm going to give it a subscript R, so you know I'm not talking about momentum anymore. This is radiation pressure is equal to I over C. And this is something we call radiation pressure. Not momentum. Okay, so this is, again, a situation where you've got an object and you've got an incoming electromagnetic wave, and that object has completely absorbed that electromagnetic wave. This is a case of complete absorption. In case of complete absorption. What if, instead of being absorbed, let's say the surface is a mirror, and instead of being absorbed by the surface, the electromagnetic wave comes in and then bounces off of the surface, and then none of it is absorbed? How would that change this particular, how would that change the amount of pressure that that wave is exerting on that wall? It would be doubled. That's exactly right. Because instead of, you can imagine, instead of that wave simply being absorbed, it's kind of being absorbed and then re-emitted. So it has to absorb it, and then it gets a double bounce because it has to re-emit it in the other direction, and it gets double the amount of reflection, double the amount of pressure. If it is completely reflected, then delta P momentum equals 2 delta U over C, and PR radiation pressure equals 2I over C. It's more. If we completely absorb, if it's reflected, you're actually imparting more momentum onto that surface. Okay, shall we do an example? Here is my laser pointer. I don't know if you can see this very well. There it is. How much pressure, as you can see this on Zoom, maybe you can see it over here. How much momentum is my laser pointer exerting on that wall, transferring to that wall? You don't have to guess, we'll calculate it. But you can guess if you like. How much do you think it is? That's okay, let's do it. It was kind of a rhetorical question, but I'm glad you thought you might want to raise your hand and answer the question. So let's do a laser pointer. Yeah, go ahead. That's right. That's right. For the Zoomers who might not have heard that question, the answer is if you had a piece of paper sitting in space and you have a light incident upon it, the light would actually, as it's absorbed and or reflected, would actually start to accelerate that paper. It would exert a force on that paper and it would start moving. That is correct. In fact, go ahead. Right. Yeah, that's a good question. I think it's related to force. Like force is like delta P over delta T or something like that. Like it's really related fundamentally to what force is. Yeah, I think that might be a better definition for what momentum is. Right, right, right. Yeah, and I think there's a clue again. This we're always going to talk about delta p's here, right? We're not really ever talking about the momentum of the wave. We're talking about how much that wave can change the momentum of something else. Right, right. That's right. There is a conservation of momentum happening there. Yeah, that is the momentum is being transferred from the wave somehow into the object. Yeah, yeah. I mean, I would call that an energy thing. I mean, momentum is really a force, right? It's really could the sun's waves knock you down, right? Whereas the sunburn comes from the absorption of the energy itself, and those two are related, but they're different in that sense. Does that make sense? Yeah. Yeah, well, it's instantaneous. It's not like it's imparting it over some delta t. It's really absorbing it in some instantaneous way. It does slow down in a medium, so it will slow down as it travels through water or glass or whatever. And that somehow is probably is related to the light wave having to bounce its way through the atoms of the thing itself, because it probably does travel instantaneously at the speed of light between the atoms in the medium, but over some average, it's slowed down as it passes through. But you're right, it's not that it's slowing down the way a cue ball would slow down when it hits something. It's a more discrete action than that. Yeah. What I was going to say about the question about the paper, this is a real method that people have used to propose to travel interstellar spacewise. If you build a big enough sail, you can make a light sail, and if you can collect enough light, it can exert enough force and momentum to that sail to actually have some slow acceleration of some fairly low mass object. And since that sail will just keep collecting light and collecting light, that acceleration will just go on and on and on, and you'll just keep speeding and speeding up. Now you'll get further and further away from the sun, and so you'll be getting less and less light. But theoretically, you could, without any propellant or fuel at all, get something moving fairly quickly towards another solar system, if you're interested. So this is real. People have thought about this stuff, and it can work. Anyway, let's get back to our example. My laser pointer has a power, I just looked it up, it's on the side, is 5 milliwatts. That is the total amount of power that's being delivered by my laser pointer to the wall. Boom, there it is. Let's do the case of complete absorption. we know that that 5 milliwatts is spread over some area. So we know that intensity is this power divided by the surface area. Again, I is the total energy per second per unit area. That's really what we're interested in. So we can calculate the radiation pressure now. PR is I over C, and I over C is just the power, total power of the laser divided by the surface area times C. Right, and so we also know that the force exerted is PR times A, and this is going to make it so that we don't even need to know really what the A is, right? PR is power over A times C times A. The A's go away. This is just power over C. If we want to know the total force exerted on the wall by this laser pointer, we don't need to know how big the area is. So we want to know the radiation pressure, we need to know what the area is. We don't know the intensity, we need to know what the area is. But the total force, the areas cancel out, and we can just calculate that without even knowing it. Okay, so this is, we can plug in some numbers. Our power is 5 times 10 to the negative 3 watts. Our speed of light is 3 times 10 to the 8 meters per second. And we get 1.67 times 10 to the negative 11 newtons. This is not a lot of force. This is, if you like your metric prefixes, 16.7 piconewtons. So the wall isn't really noticing this very much, right? The energy absorbed is more significant in terms of heating the wall up probably than the force pushing this wall backwards is. It's a very small amount. It takes a huge amount of light to be able to actually push objects around in any significant way. But it is possible. And actually, this is the minimum. Right? It could be higher than that because we assumed it was total absorption. We know, in fact, that it's not total absorption. How can we tell that it's not total absorption? You can see it. If it were totally being absorbed by the wall, you wouldn't be able to see the spot on the wall. We know that some of it at least is being reflected. Maybe even most of it's being reflected. So if it were being reflected, if it were being completely reflected, that number would be doubled. So the real number is somewhere between that number and twice that number, depending on how much of the light is actually being absorbed and how much is being reflected. Okay, great. Where are we at? 10 minutes, beautiful. Ooh, I'm going slow. All right, let's talk about non-plane waves. So far, we've only been considering light waves that are propagating in a plane wave sense. In other words, we could define a plane, let's say the YZ plane, as a function of X, where everything about the wave was constant. And then another one where everything the wave was constant here. And the whole thing was propagating through space in some planar way. You can have situations where that's not the case. Interestingly. How about, for instance, a point source of light? If you have a point source of light, you can have electromagnetic waves propagating in some spherical sense instead. And you can have, again, a region of space around that where there are no electric fields, or so there are no charged particles, where you have these electric and magnetic fields propagating through, but in a non-plane wave sense, a spherical sense. For instance, point source of light. Or a star or a light bulb that's really far away, right? As long as it's far enough away that you can't really resolve it, it acts like a point source of light, and you get the same sort of behavior from light coming off of it. So, can you write down series of electric equations for the electric and magnetic fields that satisfy Maxwell's equations that aren't perfectly planar? The answer is yes, you can. And the answer is they behave very similarly to the plane wave case, except that it's much more complicated. So I'm not actually going to write down the equations because it's not really important how they differ geometrically from the plane wave case. It's important how they behave physically different than the plane wave case. So let's think about that. The answer is yes, though. You can have Maxwell's equations satisfied by these patterns of waves. It works, but the geometry is complicated. So let's just think about energy conservation. So let's say some source has power P. Wow, we've gotten to the end of class and I've already used P in 3 different ways: momentum, pressure, and now power. Sorry about that. That's a capital P. I don't know if you could tell both of my other P's were lowercase, obviously. So this will have some units of watts. So let's say you want the intensity. So again, that's going to be some energy per second that this light bulb or star or whatever it is emitting per second, right? If you want the intensity of that source, though, how bright it looks to you, that's going to be dependent on how far you are away from that thing. The further away you get, for a plane wave, the energy density doesn't change as you move away from it because it's perfectly planar. For a expanding light source, though, that can't be the case anymore. Energy conservation says the total energy contained in this particular shell has to be exactly the same as the energy contained in this particular shell, and therefore it must be spread out much more for a shell that's further away from the source. In fact, how much energy is in a particular shell that's a particular distance away from the source? It is the total amount of energy that was released divided by the surface area of the shell that you're interested in, right? So you can write, and that is what the intensity is. The intensity at 2 different distances so let's say I1 is P, the power, divided by the surface area of, that was supposed to be a 1, the surface area of a sphere that contains the point in question, right? If you're this far away from the source, it's a surface area of a sphere over which the energy has to have been spread by the time it gets to that point. And the surface area of a sphere is 4 pi r squared. So r is a distance away from that source. The area of a sphere of radius r1 is 4 pi r1 squared. The intensity at some other point, let's say I2, is again the total power, which doesn't change, divided by A2, and that's P over 4 pi R2 squared. So intensity drops as 1 over the distance squared. If you want to know what the ratio of the intensity is at these 2 points, you can go P over 4 pi R1 squared times 4 pi R2 squared over P. Everything cancels out except for the R's. So in other words, I is proportional to 1 over the distance squared. If you double the distance to a source, between yourself and a source, you have cut the intensity, how bright that light looks, by a factor of 4. That's the classic 1 over r squared law of light. It comes from conservation of energy. As a wave expands, it has to be spread over a larger and larger surface area. Okay, let's do some examples in the 5 minutes I've got left. Example 1 from astronomy: the intensity of sunlight at Mars compared to the Earth. I know, I get exactly that excited when we do astronomy stuff. So, does anybody know what the orbital radius of the Earth is? Yes, in the right units, it's really easy. It's 1. In what unit? Astronomical units. Perhaps the worst named unit in the history of all units. The astronomical unit. You know, it's, I'll put the, it's like 150 times 10 to the 6 kilometers. But that's not even the important thing here. It is 1 astronomical unit, or AU. What is an astronomical unit is defined to be the distance between the Earth and the Sun. Or if you're more technical, the distance to the semi-major axis of the Earth's orbit about the Sun. And this is a useful number, a useful scale for talking about distances of things in the solar system. So does anybody know the radius of Mars, either in kilometers or in AU? I'm not surprised you don't. It's one of those random numbers. It is about, how technical have I gotten? I have gotten pretty technical. 228 times 10 to the 6 kilometers, or even easier, 1.52 astronomical units. It's about 50% further away from the Sun than the Earth is. Great. So how much less intense is light on the surface of Mars than it is on the surface of the Earth? That's what we can answer now with our question. The intensity at Earth divided by the intensity of Mars. This is 1 over r squared, Rm over Re, quantity squared. And since we've used really easy units like astronomical units, that I can even do that division in my head. 1.52 AU divided by 1 AU is just 1.52 squared, which, if you're putting it in your calculator, about 2.31. So sunlight is more than twice as intense. We get twice the energy, more than twice as much energy from the sun per unit area at the Earth than they do at Mars. So before you fly to Mars and try to set up your colony using solar energy, you better take this into account, because you're going to get less than half the light there, less than half the energy from your solar panels there than you do on the Earth. Okay, let's do another example. Oh, by the way, Pluto, does anybody know what IE is? This is actually an important number. The intensity of sunlight on the Earth. It's called the solar constant. And again, if you want to build solar panels on the Earth, it's an important number to know. It's how much energy you get per square meter on the surface of the Earth from the sun. You know what that number is? It is the solar constant. It's about 1360 watts per square meter. Just fun. Pluto gets less than 1 watt per square meter at 40 AU. It goes down, this is why it's just a chunk of ice out there. It gets almost no light, no energy. All right, how much time do I have? I have 0 time. Awesome. We'll do example 2 on Monday. Have a good weekend, everyone.